Hi guys, welcome back to my YouTube channel. Today we are going to discuss about Prim's algorithm. Prim's algorithm is an algorithm for determining the minimum spanning tree in a connected graph. The algorithm states that choose any starting vertex, look at all edges connecting to the vertex, and choose the one with the lowest weight and add this to the tree. Look at all edges connected to the tree that do not have both vertices in the tree. Choose the one with the lowest weight and add it to the tree. Repeat step 2 until all vertices are in the tree. Steps. Choose vertex A. Choose edge with lowest weight AB. Look at all edges connected to A and B, which are BC, BD, AD, AF. Choose the one with minimum weight and add it to the tree, which is AD. Look at all edges connected to the tree BC, DC, DE, DF, and AF. We don't need to consider edge BD because B and D are in the tree already. So we choose edge DC. Look at all edges connected to A, B, C, and D. We still have to connect E and F to the tree. So we look at the edges connected to those and choose the one with the lowest edge, I mean the weight, which is CE. There is only one vertex F to add before we have a connected minimum spanning tree. We choose edge EF and add that one to the tree. The tree is now connected and spans all vertices in the graph. Question: what is the theorem about MSTs, which are minimum spanning trees, and cut edges that applies to Prim's algorithm? Theorem of the light edge rule. The following states that the lightest edge across a cut is in the minimal spanning tree of G. Let G is equal to V E W be a connected undirected weighted graph with distinct edge weights for any non-empty U, which is not a set of V. The minimum weight edge E between U and V by U is in the minimum spanning tree MST of G of G. MST. We represented a way to write parallel code to find an MST using algorithm. The idea is simple. Instead of contracting any of edges, only contract edges with the minimum weight from edge vertex each. Why does this work? Recall the light edge rule cut property from lecture. Let's go over an example. In the first round of algorithm, we have the following flips. As you can see in the PPT, there are few highs and few tails. Notice that vertices 3 and 4 are connected but 1 and 2 are not. Why? The key point to note here is that in our version of algorithm, we only consider the minimum out edges from each vertex. That is to say, even though the input graph is undirected, we only pick an edge to be in our MHD if it goes from the tails to head. This works depending because we represent undirectedness by having an edge in both directions. We get the following contracted graph in the next round. Here is the sequence of flips generated for the second round. T, H, T, null, null, T, null, T, null, H. We will generate another sequence of 10 flips here, but we only look at the ones generated for the vertices which remain in our connected graph. This gives us this gives us this picture with the following sequence of flips, ignoring vertices not in our graph. Of course, the flips seem a little tutorials, allowing us to contract with this graph in three rounds. That is because they were made up for this example. In general, it's not unreasonable to have a round of which results in no contractions at all. This is where exception comes in. So this is it about Prim's algorithm. So we will see in the next video.